this video, we're going to be talking about the definite integral. So in class last time, we talked about Riemann sums and how you could approximate the area under a curve between the curve and the x-axis by dividing the region up into rectangles and then adding up the area of all the rectangles. As the rectangles get smaller and smaller, they more closely match the shape of the curve, and this gives us a better and better approximation. However, when we were doing that, we required the area underneath the curve to be above the x-axis so that we could more easily draw the rectangles. Today, we're going to look at some situations where the rectangles go below the curve and what this might mean for the value of the integral. We're going to be looking at what a definite integral is, as opposed to the mechanics of how to compute a definite integral. We'll be doing the computation of the definite integral in the next section when we talk about the fundamental theorem of calculus. But for today, we just want to get a feel for what is a definite integral and what does it represent in different real-world situations. So we will allow the curves to become non-negative in some cases, and that means that they'll be taking on some negative values. We'll also allow some of the curves to have a finite number of discontinuities. So that might be something like a hole in the graph, or it could be a jump in the graph. We're going to learn how to deal with those things in this issue. What we want to talk about first is the actual formal definition of what a definite integral is. So first, we start with a function, and the function needs to be defined on a closed interval from a to b. That means that the function has values on the interval from a to b, except possibly at a finite number of holes. All right. Then the definite integral of the function f from a to b is given by, and we again see this integral notation with this elongated s, but with an a at the bottom and a b at the top, and the function f of x written after the integral symbol next to the differential dx. This is defined as the definite integral, and it is the limit as n goes to infinity of the Riemann sum of the function values at a particular point inside of the rectangle, any given point, times the change in the width of the rectangles. So basically, provided, of course, the limit exists. Basically, what we have then is the definite integral, and called definite because we're going from a definite value of a at the lower level to a definite value of b at the upper level, called limits of integration. We have this being equal to the limit of a Riemann sum. Remember, the Riemann sum is approximating the area under the curve. And by taking the limit, we're allowing the width of each little subrectangle to go smaller and smaller and smaller, which makes the rectangles together better approximate the area under the curve. As the number of boxes goes to infinity, the width of each box approaches 0. Provided the limit exists, this is the value of the definite integral. It is that area under the curve between the curve and the x-axis. If the limit exists, then we say that the function is integrable on the interval from a to b, or that it is an integrable function. Now, if the area is non-negative, the function is non-negative, then that means that the definite integral is giving the area above the x-axis between the x-axis and the curve. It gives area even if it's below the x-axis, but when it's below the x-axis, we have what's called signed area. And that means that the area below the x-axis may take on a negative value because it's below. You can think of it as sort of having a negative height. The width is still positive because it's the horizontal distance, but because the function is below, the height of the rectangles are all negative, and that will give you a negative area if you add them together. Let's make sure, though, that we understand the difference between the definite integral and the indefinite integral. They are not the same thing. They are related, and the way that we compute a definite integral, as we'll see later this semester, does involve the indefinite integral, but they are fundamentally different ideas. The indefinite integral is an antiderivative function. This is a function that represents the antiderivative of the integrand. This is the function that if you were to take the derivative of it, you would get the integrand, all right? So this is a function. That means it has a variable in it, and it represents some curve in space. When we look at the definite integral also has a function in it. It does have the function in the integrand, but because it has those limits of integration on the top and the bottom of the symbol, we're actually looking at the area between the curve and the x-axis from A to B, which means that we're getting area and not a function, not an area function, actual area, as in 5 square units. What we get out of a definite integral is a number, a real finite number. What we get out of an indefinite integral is a function up to some constant plus c, which represents the antiderivative of the integrand. We're going to see later on about how these are related and how we can use the indefinite integral to evaluate the definite integral. But today, again, we're just focusing on what does a definite integral mean, and what does it mean to have area under the curve, and how can we compute that, and how do we relate that to the notation? Make sure that when you see the notation that you recognize the differences between them. The indefinite integral has an integrand here, and we have a variable here which matches the variable inside the antiderivative function. And we have the antiderivative function only up to a constant plus c. Over here, for the definite integral, notice that our result is a number. It's a finite number. There's no variable at all. So since there's no variable, it's not matching what's inside of the definite integral. And we'll actually see that the variable inside the definite integral, unlike the variable here, this one is a dummy variable. It doesn't matter what I put there. I can put anything there. It won't affect the number I get out as the result, which represents the area between the curve and the x-axis. Notice it does have these numbers attached to the integral symbol, which represent the left endpoint and the right endpoint of the region we're talking about. The indefinite integral does not have these limits of integration. Without them, we're looking at the antiderivative function. With them, we're looking at the actual value of the area between the curve and the x-axis from A to x equal B. You can think about the integral symbol as an elongated S, and that is where it comes from. It represents sigma, or the summation symbol that we used in the Riemann sums to add all the areas together. They just took the S and they elongated it. So remember, the sigma symbol looks like this. So this somehow got translated into this long S-type object. Note that it does extend above and below the line if you're using line notebook paper. It's quite large. It is not a capital S. It is larger than a capital S. If you had line notebook paper, the lines would be about here and about here, with the S extending both below the line and above the line. These numbers that we put onto the symbol in a definite integral represent the vertical lines where we're starting to evaluate the area between the curve and the x-axis, and where we stop evaluating the area between the curve and the x-axis. These are called the limits of integration. We call the one up here the upper limit of integration, or just upper limit for short. And we call this one down here the lower limit of integration, or lower limit for short. The function that follows the integral symbol and is written to the right as if it were on that line for the notebook paper is called the integrand. It is the thing that is being evaluated for the area between it and the x-axis. So when we're looking at what follows the integral symbol, this is called the integrand, the thing that is being integrated, the thing that we're trying to find the area between it and the x-axis. The variable of integration, like I mentioned a second ago, does not affect the value of the area between the curve and the x-axis. Of course it doesn't. The area is the area. It doesn't matter if I'm calling it x or t or happy face or even triangle or u. The area is the area, and it is a finite real number. So when we look at that, we have a finite real number as our value for the definite integral. So what we use for the differential and for the variable inside the integrand is completely arbitrary. Now, I will say we typically do use x, and we typically also use t and u. Those are the most common ones you see, but there's no reason why you can't use a triangle symbol or even a happy face if you feel like it. The variable that shows up in the integrand and the differential of a definite integral does not show up in the final result. And we really should have down here limits of integration on these so that they are definite integrals. So let's put some limits of integration on here, since otherwise this statement would not be true. All right. So I've got an error in my notes I'll have to fix after class. When you have a definite integral, it doesn't matter whether you have x or t or u or a triangle. When you have an indefinite integral, the variable that shows up in the differential affects the variable you use in the antiderivative. So for example, if I have the indefinite integral of f of x dx, I expect to get an antiderivative function of x. On the other hand, if I had an indefinite integral of a function of t with respect to t, then I would expect to get an antiderivative function of t up to that constant plus c. So you can see for the indefinite integral that the variable that shows up in the differential and in the integrand affects the variable that gets used for the antiderivative. For a definite integral, there is no result that has a variable in it. The result we get for the definite integral is a finite real number. There's no variable at all. And so there is no effect on the result of the definite integral. Okay. We have a theorem that says that provided the function is continuous over the interval from a to b, then f is integrable over a to b. Let's remind ourselves, what does it mean to be continuous and what does it not necessarily mean? So remember that continuity and differentiability are not the same thing. If it's differentiable, it is continuous, but we have continuous things that aren't differentiable, like the absolute value function that comes down to a point. You also have functions like x to the 2/3 that have a cusp in them, right? So this pointy part. Those things are still continuous, but they're not differentiable. So what are the three conditions to be continuous? The function exists, the two-sided limit exists, and the function value at that point equals the two-sided limit at the point. So what we're saying in a hand-waving way is, as long as I'm looking at the graph and I've got A here and B here, as long as I can draw the graph without picking up my pen between A and B, then it must be integrable over A to B. There must be a definite integral between those. In other words, there has to be an area between the curve and the x-axis. There has to be some value that you can find that is a finite real number that is the area of the shaded region that you see here. That does not necessarily mean that the function has to be differentiable. You can see that I've drawn some sharp points here. It's not differentiable there, but it's still integrable. We still have an area there. In fact, the real rule is that as long as it is continuous except at a finite number of places, then we can still say that it is integrable. However, there is a restriction on one of these types of places. So let's take a look at what that is. So if we have A here and we have B here, it is fine to have a hole in the graph, or to have a displaced point in the graph, or even, surprisingly, to have a jump in the graph. It will still be considered integrable from A to B. Now, the jump, to my mind, is the most surprising one. But in fact, it is allowed to have a jump in the graph. This is surprising because not only is this a break in continuity, but we don't even have the same limit from the left as we have from the right. So we have a different limit. A hole, we do still have the same limit from the left side and from the right side. And we have the same limit from the left and the same limit from the right at a displaced point. In fact, they're both pointing at the hole, not at the displaced point. But on a jump, we don't even have a two-sided limit that exists. But the theorem says that as long as you have a finite number of these places, you can still integrate the function over the interval from A to B. What does that mean to us? That means it still has an area. That means that we can still compute the area of this little region right here. Now, how can we compute the area when we've got these breaks in continuity? How does that work? Why does that work? Well, the idea is if there's only a finite number of them, then you have a finite number of places that are infinitely thin. How thin? Well, extremely thin, as in width of 0. How much area then is underneath that hole? Well, since the width of that is really 0 because it's a single point, then you're taking 0 times a number, and there's a finite number of zeros because there's a finite number of discontinuities. And that means we're adding 0 to itself a finite number of times, which is 0. Adding 0 to itself an infinite number of times, then we get into problems. Remember from L'Hopital's rule that that is not always going to end up being what we expect it to be. When we have 0 added to itself an infinite number of times, we don't always get the result we expect because infinity is just weird that way. But if we have a finite number of places where we add 0 a finite number of times, then it's still 0. And what it's saying is you can subtract this finite number of places from the total area under here, and it won't change the area because there's a finite number of places, they add up to 0 area. Let's take a look now at the example 1, which is using the definition of the definite integral to evaluate a definite integral from 0 to 3 of 2x minus 1 dx. We're going to use a right endpoint Riemann sum, as we were doing in class before when we were doing Riemann sums. We learned the left endpoint, the right endpoint, and I threw in the midpoint as well because I think it's important to talk about the midpoint since it is one of the more accurate ones. And we're going to use the properties of summation in order to generate this sum. So remember, the indefinite integral is an antiderivative function. It is not related to a Riemann sum, but the definite integral is the limit of a Riemann sum. So a definite integral is basically a limit. Limit of what? The limit of a Riemann sum. So what we're going to do here is we're going to start and we're going to evaluate the definite integral from 0 to 3 of the integrand 2x minus 1. Now 2x minus 1, of course, is a slanted line. Since we've chosen to do the right endpoint, remember that the formula for the right endpoint is x sub k is equal to the beginning place, which is A, plus k times delta x for the right endpoint of each subinterval. Remember that what we're doing is we're dividing the region from A to B into a certain number of subintervals. And when we talk about the right endpoint, we're talking about this place over here on the right. This is the right endpoint of the subregion to its left. The next spot right here is also a right endpoint. It's the right endpoint of the region to its left. So we're subdividing the region from A to B into little partitions. And the right endpoint of each partition we're calling x sub k. And the formula for x sub k starts with A, the leftmost endpoint, and we add k delta x, because each of these little divisions here is delta x. This means that our formula for this particular integral, since A is 0, is going to be 0 plus k delta x, or just k delta x. Now, we're using a regular partition, which I told you before is not strictly required. They do not all have to be the same width. We can take different widths as we want, but the key is whatever the widest one is, which we call the mesh, the widest one has to get smaller and smaller and smaller and eventually go to 0. As long as the widest one goes to 0, then all the smaller ones have to be going to 0 as well. But for ease of calculation, we take a regular partition just because it's easier than trying to decide how you want to divide it up. So we're going to take a regular partition, and the way we do that is we take the difference between the right endpoint and the left endpoint, b minus a, and we divide it into n subintervals. N is an arbitrary representation. It just represents the number of partitions you want to make. Maybe you make 4, maybe you make 5, maybe you make 4 million. You're partitioning that region from 0 to 3 into n size partitions, n little widths. In our formula, since b is 3 from the upper limit of integration and a is 0, this gives us 3 minus 0 divided by n, which is 3 over n. So our delta x becomes 3 over n. So our x sub k then, coming down here, is going to be k delta x, but our delta x is 3 over n. So now we have k times 3 over n. And if we rewrite it with the 3 at the front, we get 3k over n. And that represents the value of the right endpoint of each little subinterval. So if k is 1, that's the end of the first one, which would be at 3 over n. When k is 2, that would be at 6 over n. And k is 3, k is 4, and so on. We can actually compute the value of those right endpoints. Now we need to calculate the function at the right endpoint, because remember from our formula up here, what we're doing is we're taking the function and we're substituting in this special place called x sub k star into the function. The special place is for us typically either the left endpoint all the time, or the right endpoint all the time, or the midpoint all the time. Again, this is totally arbitrary. The truth of the matter is it could be any point within that subinterval, but it does have to come from that subinterval. So if I want that spot for the first one, fine. If I choose that spot for the second one, also fine. But to make it easier to compute, we try to be consistent and choose a similar value from each one. We're doing the right endpoint, so we want to take our right endpoints and plug them into the function. So we have this representation now for what the right endpoints are, which is 3k over n. And we want to take the 3k over n and plug it into our function in place of the variable x. Our function, the integrand, was 2x minus 1. So we take our x sub k, which is 3k over n, and we substitute it or x in the formula for the integrand. This gives us 6k over n minus 1. This gives us our f of x sub k star, or our special one. And then again, according to the formula, we multiply that special value by delta x. Remember that our delta x value was coming from b minus a divided by n, which is 3 over n. So now we have the expression of f of x sub k star, our special spot, times delta x, which became 6k over n minus 1 times 3 over n. Now this is just algebra, so you can just distribute this over both terms. So don't forget to distribute over both terms, or you'll see my arrows on your work. And this gives us 18k over n squared minus 3 over n. This becomes the summand, or the part that's being added together inside the Riemann sum. So this is what the Riemann sum then looks like. Here's our 18k over n squared minus 3 over n. This is the summand. I know it's a weird word that we introduced last time when we were talking about Riemann sums. It is the thing being summed, basically. That's what it means, the thing being summed. And we're going from k equal 1 to n. Now, to get the actual value of the definite integral, when we're done doing the Riemann sum, we're going to take the limit of it as n goes to infinity. So now what we have is we want to split the summand up into two different sums. So we use the properties of series in order to split the sums into two sums. So we get the sum of 18k over n squared minus the sum of 3 over n. Now, the trick to remember about Riemann sums is that the only thing that can't pass through the symbol itself is something that depends on the index. Our index is k. So k cannot come out of the summand because it's not a constant. As far as the sum is concerned, it's the variable. So, but that means that n squared and n here, and even the 3 and the 18, those are constants. As far as the sum is concerned, they're not the variable. The variable for the sum is the index of summation, which is k. So we can pull the 18n squared out, which just leaves behind the sum from k equal 1 to n of k, minus the 3 over n times the sum from k equal 1 to n of 1. Now, we learned last time that there are some formulas to help us compute some of these sums. And one of them is this one right here. If you have the sum from k equal 1 to n of a constant, then the result is the constant times the upper limit of summation, which gives us n. So we have 3 over n times n. The first one is the sum from k equal 1 to n of k, and there's a formula for that too. It becomes n times n plus 1 over 2. And we talked about this when we were talking about Riemann sums. Now we just do some algebra again to simplify what we have, and we end up finally, after quite a bit of simplification, down here with 6 plus 9 over n. This is our final simplified format for the Riemann sum. By definition of what the definite integral is, since we are trying to compute the definite integral again, we're trying to compute the integral from 0 to 3 of 2x minus 1 dx using the definition. And the definition is the limit of the Riemann sum. So we let the number of rectangles, the number of partitions, the number of little widths we cut it into go to infinity. The more we use, the more accurate it is. And so now we need to take the limit of the Riemann sum that we found. So coming down here, our next step to evaluate the definite integral from 0 to 3 of 2x minus 1 dx is to take the limit of this sum. Now I've used x here inside the integrand and inside the differential. I could just as easily have written this with any symbol at all, because it's going to disappear from the value of the limit. the limit is going to give me a finite real number, there will be no variable present at all. So I could just as easily have written something like this, which is kind of shocking to a lot of students. They're not used to seeing something like this, but there's no reason you can't use a happy face for your symbol inside of a definite integral. It's a dummy variable. It shows up in the middle. It helps you get to the end, but it doesn't show up in the end. So it's sort of like an interim on the way variable that's going to go away again. So it doesn't matter what you use because it's not going to show up in the final process. So now we take the limit of what we got for the Riemann sum, which was 6 plus 9 over n. And you know that a constant divided by n, as n goes to infinity, is going to get driven down towards 0. No matter how large the constant is, infinity is so massive that it eventually overpowers it and practically drives it to 0. Practically. Does it ever actually get there? No, but that's the beauty of the limit. It doesn't have to. That's what it looks like it's going to be. So that's what it is. And this gives us the value of 6. What does the 6 mean? Well, the 6 means that we've got area under the curve of 2x minus 1 between 0 and 3. And that's what we've got. So when we're looking at that, we're going to be taking a look at how to do that. So when we're looking at the curve and we're going from 0 to 3, we're actually getting the area under that curve. Let's take a look now at the next part. Until we find a better way of calculating definite integrals, we're going to be using geometric figures and formulas to calculate the area. Now, okay, I know that's crazy. First off, most areas don't lend themselves well to geometric figures. And second off, that's incredibly tedious and will take forever. So we only do it this way for about one section. And then we learn a better way of calculating the definite integral, which ties together the two fundamental ideas of integration. It takes the antiderivative and weds it to this idea of the definite integral, which represents the area under the curve. And it gives the relationship between the two. Let's talk about how we can use geometric formulas to find the area and evaluate a definite integral. Why do we teach it this way if there's a better way? We want students to get the understanding that what the definite integral is this area under the curve. It's really important to grasp that. Let's look at this problem. In example 2, we want to use the formula for the area of the trapezoid, 1/2 base 1 plus base 2 times the height, to evaluate the definite integral from 2 to 4 of the function 2x plus 3 dx. So what are we looking at? Well, when you look at the picture, you can see that the function right here, 2x plus 3, is graphed on top. And the region between 2 and 4 has been shaded green in the picture. So what we're talking about with the definite integral is the area of that region. So how can we use the trapezoid formula to find it? Remember, a trapezoid means you have a 4-sided object. 2 sides are parallel, 2 sides are not parallel. So when we look at the trapezoid here, let's evaluate which of the sides are the parallel sides and which ones are the non-parallel sides. So when we're looking at the trapezoid, you can see that the top is clearly not parallel to the bottom. So these are the non-parallel sides. And the parallel sides are the sides that correspond to A and to B. So this would be the x equal 2 and x equal 4 from our definite integral, the lower and upper limits of integration. So what we want to do is we want to apply the formula to this particular function. So we need to find the height at base 1 and the height at base 2 and multiply by the height of the trapezoid. But the height of the trapezoid is the distance between the parallel sides. So you almost have to take our formula here and rotate it sideways in order for it to be a height like we're used to seeing. So in other words, what we're looking at here is the height is the distance between the two parallel sides. That's the h from the formula. Base 1 and base 2 then are the lengths of the two parallel sides. Those are the bases. So now pause the video, compute the area using the formula, then turn the video back on and see how you did. How did you do? Let's take a look and see what I did. B1 is the length of the left side, which is at 7. Now, how did I know it was at 7? Well, the upper function is the integrand function, and that's 2x plus 3. So I looked at the left side and saw that it was at x equal 2. So I took the 2 and I plugged it into the formula, which gave me 7. That means that the ordered pair 2, 7 is here. So the length of this side is 7 long. I did the same process to find the length of the right side, which I found to be 11. Then I was able to look at the bottom to find the distance between the two parallel sides, which is the distance between 4 and 2, or 4 minus 2, which gave me 2. When I plugged it into the formula then, I found that the value of the definite integral from 2 to 4 of 2x plus 3 dx is 18. 18 what? 18 square units. This is area. So this represents the number of square units that we have. Let's take a look at the next example. In example 3, we're to evaluate the integral of the function graphed in the image by using the formula for the area of a circle, which is pi r squared. Now let's first connect what we see in the picture to the notation for the definite integral. Notice that these are not the same function. These are 3 separate functions, and we need to connect their ideas together. So what we really have are 3 separate definite integrals. We have the definite integral from 0 to 2 of the function, the square root of 2x minus x squared. That's the first definite integral that we have. Now, do I have to use x? No, I don't, because when I'm doing this and I get to the final result will be a finite real number, which will have no variable. So the variable I use is arbitrary. For the second one, notice that it goes from x equal 2 up to x equals 6. So this is the integral from 2 to 6. And this function right here, which represents the upper hemisphere of this circle, is my function's integrand. So this gives me the integral from 2 to 6. And for fun, let's just change the integrand variable from x to t. Will it affect the value of the definite integral? No, it will not. It is the same if I integrate with respect to t as if I integrate the same function with respect to x. The area between the curve and the x-axis is the same. The final integral that we have is one that extends from 6 up to 12. And again, we'll use a different variable of integration just because we can. And just to hammer home for you that it does not matter what you choose, that the value of the definite integral is an area. So this is going to give me the integral of negative 72 plus 18u minus u squared, and we'll make the differential then du. So this connects the idea of the definite integral as the area from x equals 0 at the lower limit to x equal 2 at the upper limit of this function graphed in the plane, plus the area of this function graphed in the plane from x equal 2 to x equals 6, plus the area of this function graphed from x equals 6 to x equals 12. Now you know that the area of a circle is pi r squared, so go ahead and pause the video here and compute the areas. Now for those of you who are going, but I don't know the radius, of course you know the radius. Look at the picture. The picture's telling you what the radius is. You can find the midpoint, and then go over to the edge. But you can also realize that the height of each of these hemispheres or semicircles is actually the radius. So you can find the radius off of the graph. Pause the video and compute the area, the value of the definite integral. Let's see how you did. If you're looking at the pictures, you can see that I've labeled them with the value of their radius, r equal 1, r equal 2, and r equal 3. Then I computed the area, which is equal to the sum of the three definite integrals that we have here, as pi times 1 squared plus pi times 2 squared plus pi times 3 squared, which gives us 14 pi. Let's take a look at the next example, and this time we'll let you do more of the work. In example 4, we want to evaluate the integral of the function graphed in the image you see here using the formula for the area of a triangle. Remember that the area of the triangle is 1/2 the base times the height. When you're doing the formula, you'll have to find the height of the triangle by looking at the graph and thinking about the value of the function at the top of the triangle. Go ahead and pause the video and turn the video back on to see how you did. Try writing down the formula and the notation for the definite integral to accompany this picture. What you get for your result? I got 14 square units. So I wrote the definite integral from 0 to 2 for the first function, plus the integral from 2 to 6 for the second function, plus the third integral from 6 to 12 of the third function. Each one was computed using the formula for the area of a triangle, 1/2 the base times the height. And I came up with 14 square units. Well, let's take a look at what we mean by area and the definite integral when we allow the function to go below the axis. What does that mean? If we allow it to be negative and it dips below, what is that going to do to the area? This is what we call net signed area. When you take some of the rectangles and you put them below the axis, the width of the rectangle remains positive, but the height of the rectangle, because it's below the axis, becomes negative. And that makes that area negative. So when we say net signed area, what we mean is the area above the x-axis is positive, and the area below the x-axis is negative, and the net signed area is the combination of the two, positive above and negative below. We can also think of this as the area of the rectangles that are above the x-axis minus the area of the rectangles that are below the x-axis. It means the same thing. You're subtracting the area from below the axis from the area that's above the axis. This gives us A1 minus A2 if we consider the areas themselves to be strictly positive. And that gives us net signed area as we allow the number of rectangles to increase to infinity. Notice that your net signed area could be positive if you've got more area above the axis, or it could be negative if you have more area below the axis. It can even be 0. If you have exactly the same amount of area above the x-axis as you have below it, then your net signed area will be 0. What is the definition of net signed area? Well, it turns out that the definition of net signed area is simply the definite integral. It will automatically take care of the sign. So what we're looking at here is the definite integral from a to b of f of x dx, which gives us net signed area, a1 minus a2. This is provided that f is an integrable function and that it's defined over the closed interval from a to b, except possibly at a finite number of points. Now let's take a look at example 5. In example 5, we want to find the net signed area of the function x minus 2 over the interval from 0 to 6, which is what you see here in the picture. Now you should have an expectation already that because there's more area above the axis, that it should end up with positive net signed area. This part here is going to be negative because it's below. We're going to use the formulas for triangles to compute the net signed area. In order to do this, you'll have to figure out how wide the base of each triangle is and what the height of each triangle is. But realize that these points that are on the curve are on the function x minus 2. And that means that we can use the x coordinate there to compute the y coordinate there, and that will give us the height. Pause the video, do the work, write out what you believe the definite integral should be, then turn the video back on and check your answer with mine. Let's see how you did. Note that there are a couple ways of thinking about it. You can either think of the triangle below the axis as having a negative height, or you could think of it as having a positive height, but because it's below, the area itself is negative. Both ways work, and both are correct ways of thinking of it. When you compute the areas, notice that you have to find the function values of the 3 points. This then gives us the final result of 6 square units. Let's look at the next example. In the next example, we're to find the net signed area of a function over the interval from 0 to 12 in this image here. We already know that the formula for the area of a circle is going to be pi r squared. Don't forget to divide it by 2, which I now realize I forgot to do in the one up here. So let's fix that now. In the previous problem up here, I forgot to divide everything by 2. So this should have been divided by 2. Why? Because I only have half the circle. So those of you who figured that out before me, kudos to you. You'll have to excuse me, it's a little late. And so I'm probably a little bit tired. So let's keep going. Don't forget to divide them by 2 for the next part. Pause the video, do the work, and then turn the video back on to check your answer. How'd you do? When we look at this one, you'll notice that we again have 3 different regions because we have 3 different functions. And because we have 3 different functions, we have different integrands. So we need 3 different definite integrals. The first is from 0 to 2 for this half circle that we see here. The second is from 2 to 6 for this upside down absolute value that we see down here, which forms a triangle. And then we have this half circle that we see here. And you'll notice that I chose to change the variable of integration in the differential and the function to t instead of x. It won't make any difference in the answer. The answer is an area value, which is a constant. This gives me the formula of 1/2 pi r squared because it's a half circle for these two, and 1/2 the base times the height for the area of the triangle for the one in the middle. Notice that only the one that is below the axis is negative and the others are positive. 10 pi divided by 2 reduces to 5 pi. Now let's talk about total area. Total area is different from net signed area. Net signed area means area above the axis is positive and area below the axis is negative. Total area looks at just total area. How much space would you need to paint? So how much paint do you need? It doesn't matter whether it's above the axis or below. In other words, it's looking at the absolute value of the area, and that's what it's computing. So when we talk about total area, we're talking about the region you would need to cover with paint to shade in all the shaded region between the curve and the x-axis. This makes it the absolute value of the integrand. And this doesn't give you A1 minus A2, where A2 is below the axis, but instead A1 plus A2. So it's the sum of the two areas. So total area is the absolute value of the integrand, and net signed area is just the integrand. Let's take a look at what difference it makes when we compute that in example number 7. To find the total area between the function f of x equal 2x and the x-axis over the interval from -3 to 3, we need to think about the amount of area that we have both above and below the axis and simply add the two together. Now, we're looking at the function that we have here, which is 2x, and we want to integrate between -3 and 3. So that becomes our limits of integration. That means because I'm looking at total area, that I need to put my integrand into absolute value. The differential does not go into the absolute values, just the function itself, which is the integrand. This will represent the total area, the region that needs to be shaded, whether it's green or purple. When I'm looking at it on this particular problem, I can look at the region and realize that this point right here is at 3, 6, which means the base is 3 wide and 6 tall. So the area of the green is simply 1/2 the base, which is 3, times the height, which is 6. Then I look at the region that's below the axis, and I can do this one as well. This is also 3 wide, coming out to -3. And when I look at this point down here, this point is -3, -6, which means that I also have another triangle, which is 3 wide and 6 tall. I can think of it as absolute value, stripping it of all sign, and then it becomes positive. And I don't know why I put a 3 there. That's supposed to be a 2. So what ends up happening is we end up with 9 plus 9, which is 18. I would need 18 square units of paint to paint the total area, whether it was above the axis or below. What does this have to do with displacement and the distance that's traveled? Well, one of the applications of the definite integral is to find the displacement of an object that's been traveling for some length of time, and also to find the total distance that the object has traveled. Now, these are not the same thing. So imagine that you're at home and you drive from home to Colorado Springs, and then you drive back home. You may have driven a distance of about 160 miles, but your displacement, since you're back where you started, is 0. If you're back where you started, you're back to displacement of 0. Now, what would it mean if you lived here in Lakewood and you drove to Denver and then to Colorado Springs and then you drove back to Denver, but not back home? Well, then your displacement would be 10 miles because you're 10 miles from Lakewood to Denver, but your total distance traveled would probably be about 150 miles, not the full 160. So total distance traveled is more like the idea of total area, and displacement is more like the idea of net signed area. Let's see what this has to do with the graph. If we think about velocity as a constant function, where this line represents the velocity here along the vertical axis, and we have time along the horizontal axis. If we have a constant function here, then putting this underneath the curve basically means that we just have velocity multiplied by time. Well, velocity multiplied by time is distance. So that would give us the distance traveled. So this would be the constant velocity of 70 miles per hour times 2 hours of travel, which would give you a displacement for the object of 140 miles from where it started. When you put this into the definite integral format, you get the integral from time equals 0 to time equal 2 of 70 miles per hour integrated with respect to time, and you get 140 miles. Again, this is the idea of displacement, your total displacement from where you started. This is like the idea of net signed area. Total distance traveled is more like total area. Let's take another thought about the displacement of an object which traveled for 2 hours at 60 miles per hour, then turned around and drove in the opposite direction, negative velocity at 40 miles per hour for 3 hours. The net signed area will tell you that you have 0 miles of displacement. The object ends up right back where the object started. Let's take a look at the picture that represents that. In the picture, what we have is 60 miles per hour driving in the positive direction because it's above the axis here. So it's positive velocity for 2 hours. So that would give me a distance traveled of 120 miles. And that distance would be the displacement during the first 2 hours. In the next 3 hours, however, it drives in the opposite direction. I know because velocity is below the axis. So it's driving the opposite direction at 40 miles per hour for 3 hours. The displacement is 120 miles from where it was, but it puts it right back where it started. Because if you go 120 miles in one direction, and then you come 120 miles straight back, you end up where you started. And the total displacement then is 0. To represent it in the definite integral, we have the integral from 0 to 2 of 60, and 60 is positive, plus a negative 40 being integrated from 2 to 5. This gives us 120 miles minus 120 miles, or 0 displacement. In the second situation, if we wanted to talk about the total distance traveled, the total distance traveled would be the absolute value of the areas, like the total area. And that would give you 120 miles plus 120 miles, which is 240 miles of travel. You'll definitely feel like you've been in the car a long time. You just ended up back where you started. So again, when you apply the absolute value, you're looking at total distance traveled, not net displacement, not how far are you from where you first started when you began traveling. Let's now take a look at the properties of the definite integral. If the limits of integration are the same, then the integral is just the area under one single point, meaning it is just a vertical line. And since the width of every vertical line is 0, then it becomes what we call a trivial rectangle or a degenerate one, where the width is 0, so it has no area. This is like the definite integral from a to a of f of x dx. Notice that the lower limit of integration and the upper limit of integration are the same number. And because they're the same number, we're talking about how much area is under one single point. Well, the area under one single point is 0 because the width of the box that's there is 0. If I go from a to a minus a is 0. Divided by n is still 0. So the width is 0, so the area of the rectangle is 0. That's the first property of the definite integral. The second property has to do with switching the limits of integration. If you switch the limits of integration, you're integrating backwards in a sense. Instead of going from a on the left to b on the right, you're integrating from b on the right to a on the left. So you're going backwards, which means your width has a negative value. So you throw in a negative onto the integral. So if you switch from a to b and go from b to a, it just throws in a negative into the definite integral. That means that you can rewrite anything where you don't like the order. For example, let's suppose the order was 3 to 0 of some function of x with respect to x, and you don't like that order because you're used to the lower limit of integration being the lower number. You can switch the order, and again, these do not have to match variables as long as you put a negative out in front of that integral. Then you can switch the order of the limits of integration. This is really handy when you have lots of negatives running around. It can really save you a lot of grief. The next property of the definite integrals is that the integral of a sum or a difference is the sum or difference of the integrals. In other words, you can split the integral across things that are being added or subtracted together. So if I have one function plus or minus another function, I can split the single definite integral into two definite integrals where I do the integral of f of x and then I do the integral of g of x. Now, this only works for addition and subtraction. Do not do this for multiplication and division. It does not work. It only works for addition and subtraction. In that sense, it's similar to the derivative, where the derivative of a product is a whole nother rule, and so is the derivative of a quotient. And you'll find that we'll spend a lot of time in Calculus 2 talking about how to deal with integrands that have products and quotients in them. A lot of time. The next rule that we have has to do with a constant being multiplied by the function that is the integrand. If the integral of the product of a constant and the function is in the integrand, then we can pull the constant out of the integral. A constant being multiplied by the function, in other words, simply does not change the way that the area is computed, and you can multiply the area by the constant after you're done. And so this can also simplify some of the work that we do, as you'll see when we start the true method of computation of definite integrals, which is not using geometric formulas. The next property normally is applied when C is between A and B, but it actually holds whether C is between A and B or not. So it works no matter what, as long as the function is integrable on the largest possible interval. So this says if I want to integrate from A to B, I can break it apart at any number C and integrate from A to C and then C to B. So when do we usually use this? Usually I might use this if I want to integrate from 1 to 5 of some function. I could split it and I could integrate from 1 to 2 of the function. And then I could add to that the integral from 2 to 5. And you can remember that we've done this already multiple times today. When we had different functions, we split it and we just integrated over each individual different function. And we can do this as well. Then we have what are called some comparison theorems. The comparison theorems basically give us the relative sizes of these areas that we're computing. This says if the function is always greater than or equal to 0, well, then the function is always above the x-axis. And if that's the case, then the area should definitely be strictly positive as well. If it's just greater than or equal to 0, then the area should also be greater than or equal to 0. The next one says, well, if f of x is greater than or equal to g of x, then the area between f of x and the x-axis should be greater than the area between g of x and the x-axis. If you think about this one, you can think about having two curves. We'll call this one f of x. And then we can have another curve below it. We'll call this one g of x. Well, it should make sense to you that the area that is underneath g of x has got to be less than the area that is underneath f of x, because f of x is larger and it includes the area that's under g of x plus more. And so you can see that as long as f of x is greater than or equal to g of x, then the area between f of x and the x-axis is greater than or equal to the area between g of x and the x-axis. This brings us to our final comparison in the comparison theorem, which is suppose I have two constant numbers, m lowercase and m uppercase. These are constants. These are numbers like 42 and 3033. When we look at these two constants, if our function's value for y is always between these constants, then the area for it will have to be between that constant multiplied by the width of the interval. In other words, this is sort of like taking the area of a rectangle of height lowercase m and width b minus a, and another rectangle of height uppercase m and width b minus a, and saying, well, if m is always bigger than or equal to the function, and the function is always bigger than or equal to lowercase m, then certainly those areas are the same. So when we think about this particular one, we can think about drawing a curve again. So here's my function for f. And then somewhere up here, I have an m. And m is always the same value. It's a constant. And then down here at the bottom, I have a lowercase m, and it's always the same value. And then I need to find out where a and b are. So if a is here and b is here, then what it's saying is if I divide this region right here, then I've got a certain smaller amount of area here. This is b minus a times lowercase m, the area on the far left. And I've got a larger area here. If I take that area underneath there, underneath the uppercase m, and the one for f has to fit in between. So f is sort of in between the two. And let's make it blue. So the area for the function is between the areas of these two rectangles that you see on either side. Let's now look at example 8. Example 8 wants us to use the properties of the definite integral to express the definite integral of this function over the interval from 1 to 3 as the sum of 4 definite integrals. Well, there are infinitely many ways to divide this up because there are infinitely many numbers. Here's one way. We could divide from 1 to 1.5. And to save time, I'm just going to write f of x dx plus the integral from 1.5 to 2 of f of x dx plus the integral from 2.5 to, I need to stop because these need to connect. So I need to start at 2 and go to 2.5 of f of x dx plus I could do the integral from 2.5 to 3. I've still covered the same region from 1 to 3. And this is one way to do it. But they don't have to stay in order. I could actually integrate from 1 to 10 of f of x dx as long as my next integral goes from 10 back to 3. This will bring it back around and correct the values for the area that you included that should not have been included. It will take it back out again in a sense. So it is okay to use a number that's not between a and b, but I would say that it's pretty atypical to do that, but it is okay. Now let's take a look at the next example, which is number 9. It is known that the integral from 1 to 5 of the function is -3, meaning it has more area below the axis as above, and the integral from 2 to 5 of f of x dx is 4. So it asks the question, what's the value of the integral from 1 to 2? Well, the first thing that we can realize is that the integral from 1 to 2 of f of x dx plus the integral from 2 to 5 of f of x dx has to be equal to the integral from 1 to 5 of f of x dx. And that means that I can look for the value of this first integral by replacing the values of the other two, which are known. So the integral from 1 to 2 of f of x dx plus 4 has to equal -3. If I subtract 4 from both sides of the equation, this tells me that the integral from 1 to 2 of f of x dx has to be equal to, well, I suppose it's got to be a -7. in order for the value from 1 to 5 to be -3, and from 2 to 5 to be 4, then from 1 to 2, it's got to be -7. Let's turn our attention now to the average value of a function. You know, when you do exams, that you can take all the scores on an exam, add them up, and divide by the number of exams, and that will give you the average on the exams. You can do that because there's only a discrete number of exams. There's a discrete number of students. We don't have 32 and a half students, we have 32 students. But if you have a function that gives an object's velocity at a point in time, how do you do that? Because velocity is a continuous function, it has a value at every possible moment in time. So I don't have a discrete number of points where I can take the values and add them up. So what we do instead is we subdivide the interval and we approximate by taking a sampling of the velocities in each time interval. Now, since there's a finite number of subintervals, we add those together and divide by the number of subintervals. Then we take the limit as the number of subintervals goes to infinity. Sounds like a Riemann sum, doesn't it? It does. So what we've got is the sum of all the function values divided by the number of intervals that we took. Then we take the limit as n goes to infinity. But while we're doing this, we also know that delta x is equal to b minus a divided by n. That's the formula that we use for Riemann sums. If we take this formula and we solve this formula for n instead, then we have the relationship that n is equal to b minus a divided by delta x. That means that I can substitute that in the expression for the average value. Instead of using n, I can use b minus a over delta x instead. That makes this a complex fraction, and the denominator of the denominator should be in the numerator, so the delta x flips up to the top. And it actually becomes a Riemann sum. This is the function value at a particular point in a subinterval multiplied by the width of the subinterval, and we're summing them up. It's a Riemann sum. We're also dividing by b minus a, but b minus a does not depend on k. So it can be taken out of the summation, and in fact can even be taken out of the limit because the limit only depends on n. And that gives us 1 over b minus a times the limit as n goes to infinity of the Riemann sum. Because the Riemann sum and the limit of it is the definition of the definite integral, we get an expression for the average value of 1 over b minus a times the definite integral from a to b of f of x dx. This is the average value. Now, average value would be as if every point on the function had the same function value. That is, the function only produced a single horizontal line. And then computing the area really would be finding the area of a rectangle. So you can think of it as, what would the rectangle's height be if it formed a rectangle with the same area as the area between the curve and the x-axis? That's what the F average is giving you. The definition then formally for the average value of a function is to take a continuous function over a closed interval from a to b, and the average value is given by 1 over the width of that interval times the definite integral, which represents the area. In a way, what you're thinking about is you're taking the area and dividing by the width, which should give you the height of a rectangle if that's what you were looking for. Let's now look at problem number 10. Problem number 10 is a reference back to example number 2, where we were computing the area between the curve 2x plus 3 and the x-axis between x equal 2 and x equal 4. In other words, the definite integral from 2 to 4 of 2x plus 3 dx. We use the formula for a trapezoid to do that. Let's take a moment and go back to example 2 and find the value that we got there. In example 2, we found that the result of using the trapezoid was 18 square units. Coming back now to example 10, what we want to do is we want to take the value of this definite integral and compute the value of the average value. So we're going to use the formula f average is equal to 1 over b minus a times the integral from a to b of f of x dx. For us, since we're going over the interval from 2 to 4, this will be 1 over 4 minus 2 times the integral from 2 to 4 of 2x plus 3 dx. Using the formula for the trapezoid, we got that this part was 18 square units. Now we need to multiply that by 1 over 2. That gives us 9 square units. What does that mean exactly? Or not 9 square units. It gives us the value of 9, which is the average function height. What does that mean? Well, if we look at this picture here and we shrink it down a little bit so it all fits on the page, it means if you come up here and you make a rectangle at height 9, then this rectangle right here, outlined in blue, has exactly the same area as the green shaded region. So the average height is this height right here, which is 9, right? So to summarize what we've discussed today, we've discovered that the definite integral represents the area between the curve and the x-axis. Net signed area allows the area above the axis to be positive, the area below to be negative. Total area takes the absolute value of the integrand and considers all areas to be positive. We saw that displacement is more like net signed area. It tells you how far the object is from where it started. Whereas total distance is more like total area, in that it gives the total distance traveled when you take the absolute value of the integrand. And finally, we've discovered that the average value can be found by taking the value of the definite integral and dividing it by the width of the interval. That would give you the height of a rectangle with the same area under it as is between the curve and the x-axis. I hope this helps you to do the homework, and I hope to see you in class next time.